This is Daryl with Cisco Hands-On Training. Today we're going to start our coverage of BGP with, I'm afraid, a theory class. So no hands-on today. It's March 14th, 2008. My website's at www.darylroot.com. I have these podcasts there, and I will also put a PDF of this presentation there. I have a book recommendation. I've mentioned this book before. Routing TCP/IP Volume 2 by Jeff Doyle and Jennifer Carroll from CCIE Professional Development. I used that book heavily when I was training, and I also used that book when preparing for this presentation. So I thank them for writing the book, and I encourage everybody to buy it. It gives a great understanding of TCP/IP and BGP with a good theoretical understanding plus great examples. We have studied several interior gateway protocols, IGPs. Interior gateway protocols are designed to be used inside an autonomous system. So it's designed to be used inside a company or inside an ISP. RIP, the examples, RIP was hop count based, IGRP had an improved metric but was Cisco proprietary. OSPF is a link state protocol. It provides fast convergence. It requires a specific topology. Specifically, you have to route all of your areas through area 0, and it's difficult to filter in OSPF except at area border routers. All of these interior gateway protocols assume that you trust all the routers inside your domain. You can do some filtering, but the filtering is primitive, and basically it's designed that if a router is doing something bad, well, you have control over that router, so you have the ability to go stop it on that router as opposed to just filtering. Routing on the internet has different requirements. One requirement is scalability. The internet route table is now 250,000 routes. If you put 250,000 routes into an OSPF domain or a RIP domain or an IGRP domain, those routing protocols would melt down because they just can't handle it. In addition, routing on the internet requires advanced filtering between different organizations that don't trust each other. And by don't trust, I don't mean that you believe that they're going to do something evil deliberately, but when you're running the network for an enterprise, you are in charge of the network for that enterprise, and if you connect to another enterprise or an ISP, they don't have your business interests at heart, they have their business interests at heart. Let's talk about what an autonomous system is. An autonomous system is a group of routers run by one organization. For example, AT&T is an autonomous system, Carnegie Mellon University is an autonomous system, Intel is an autonomous system. Each autonomous system might include thousands of routers. In fact, you can bet that the AT&T autonomous system probably has tens of thousands or maybe even 100,000 routers. Each autonomous system could use a different interior gateway routing protocol with a different metric inside of it. So AT&T, for example, might use OSPF internally, Level 3 might use EIGRP internally, CMU might use ISIS internally, Intel might use RIP internally, although frankly large enterprises don't use RIP, but hey. The point is that each autonomous system could use a different routing protocol with a different metric. You cannot compare metrics from different routing protocols to each other. For example, cost in OSPF has absolutely no relation to hop count in RIP or to the total metric distance in EIGRP. So you can't compare metrics between the autonomous systems. In addition, these are different companies. These are different organizations. You can't there's no governing body for the internet which says everybody has to use metric X. And on the internet, you can't just say on Tuesday, March 18th, we're all going to change our routing protocol from routing protocol A to routing protocol B. Internally, you can't impose that. So you have to cope with the fact that different autonomous systems are using different routing protocols internally. But you still need to be able to route between them, so you need to pick a routing protocol to talk between them. Okay, so that's an autonomous system. An autonomous system is a group a network, a group of routers run by one organization, and the point of BGP is to route between different autonomous systems, between different organizations that don't necessarily trust each other. Okay, we talked, in fact, I went a little bit ahead. We talked a bit about this slide. Different autonomous systems need to exchange routing information despite having different routing protocols in each autonomous system, different metrics in each autonomous system. The autonomous systems don't trust each other. There's no enforced hierarchy in autonomous system to autonomous system connections. It's not like OSPF in your company where you enforce a hierarchy through area 0. In the internet, you can connect to half a dozen different autonomous systems, each of which can connect to half a dozen different autonomous systems in a random manner, and the routing protocol needs to be able to handle that. And the internet route table is 250,000 routes and growing, which is huge. So we need a solution. We talked about IGPs, interior gateway protocols. There's another class of routing protocols called exterior gateway protocols. There are only 2 exterior gateway protocols in existence that I know of. One is the original EGP exterior gateway protocol, which is now obsolete. It was classful. It required hierarchy on the internet. Now we have a new one called Border Gateway Protocol. We're currently at Border Gateway Protocol version 4. Border Gateway Protocol is optimized for scalability instead of convergence time. So Border Gateway Protocol actually converges slower than most IGPs. It can take minutes or tens of minutes for Border Gateway Protocol to converge on the internet, but it can handle 250,000 routes. Whereas in OSPF, they try to get OSPF to converge in under 30 seconds, but OSPF cannot handle that many routes. Border Gateway Protocol has advanced filtering features where you can filter not just based on IP address, but also based on autonomous system. You can say, I don't want to accept any routes that go through autonomous system 65,537, for example. Border Gateway Protocol uses an autonomous system path list to avoid loops. So in the route information, it keeps track of which autonomous systems that a route has passed through to get to you, and in a list, and that way if a router is in autonomous system 65,000 and it sees that autonomous system 65,000 is already in the path, the autonomous system path that it receives in a route, then it knows that if it accepted that route, it would be a loop. And so that's how it avoids loops. In addition, the Border Gateway Protocol uses the number of autonomous system hops as sort of a universal metric. If the route goes through 3 autonomous systems to get to you, that's the autonomous system path size is 3 autonomous systems. Okay, one reminder, the goal of any routing protocol is for routers to exchange routing information. So our goal here is to exchange routing information between different autonomous systems. And Border Gateway Protocol has been expressly designed for that purpose. I was at a Cisco Networkers conference years ago, and one of the speakers, I don't remember his name, got up and said that BGP is a simple protocol. And at first I was shocked. At first I didn't believe him. But he convinced me. And he's right. BGP is a simple protocol. Why is it simple? Well, the first reason why it's simple is because it uses TCP for reliable router-to-router communication. So TCP handles the reliable delivery. It makes sure that each message gets to the destination router exactly once, not 0 times, not 2 times. And so BGP doesn't need to implement any sort of retransmission mechanism inside it. It just sends the data in a TCP socket. There are only 4 message types in BGP. There's opens, Keepalives, updates, and notifications. That's it. There's only 6 protocol states. We'll talk about the protocol states. And there's many filtering and prioritization options, but each one is technically simple. So it feels like it's sort of complex when you're looking at all the different ways you can filter, but hey, a filter is a filter. So BGP is a simple protocol. it's not, the problem is there isn't much BGP skill because you don't deal with BGP much. At least in enterprises, even in a large Fortune 100 enterprise where you're responsible for the border routers, you might make half a dozen BGP changes a year. And that's just not enough, that's not enough BGP changes to build up proficiency. So a lot of people sort of feel like BGP is a black art because they don't deal with it much, and the consequences of messing it up can be literally global, but BGP is a simple protocol. And I hope to convince you of that over the next few podcasts. BGP uses a TCP port. The first thing is that BGP uses a TCP port for router-to-router communication. The services provided by TCP include retransmission of lost data. It includes no duplication of data. It includes checksumming, so that way the data is transmitted accurately. So BGP doesn't need to implement all of that stuff. It lets TCP handle it for it. One note, however, TCP socket is always from one router to a second router. There are no broadcasts in BGP. There's no multicast. It's not like RIP or OSPF where you dynamically form neighbors with everything on that link that's configured for it. In BGP, you have to explicitly connect between router A and router B, and you have to configure that. And we'll see that in the configuration examples in the next podcast. There are 4 BGP message types. The first one is open, and it's used to initiate a BGP session between 2 routers. The open message goes through the TCP socket. So first you open up a TCP socket of the remote router, you get the TCP socket open, and then you send a BGP open message through the socket. The open message includes the BGP version, the sender autonomous system number, the hold time, which is how long the BGP session will stay up if it does not receive a message. The Cisco default is 180 seconds, so if a BGP session does not receive any type of message within 180 seconds, then it's assumed to be a failure and it shuts down. The BGP identifier of the sending router, which is generally the highest loopback address, if there is a loopback address, and optional parameters. And the nice thing is, one of the things that keeps BGP simple is that there is not complex negotiations. If a router sends a BGP open and you receive it and you want to reject it because you don't like the BGP version number, for example, you just send a notification message and terminate the BGP session. The other router has to figure out that's why you terminated the session and then open up a new one with different parameters. So there's no complex negotiations in BGP. If you receive an open message and you don't like the options, you just reject it and let them try a different open. BGP message type 2, Keepalive. This is the simplest message. It just says, hey, I'm still alive. Let's keep this BGP session open. You send, Cisco routers send 1/3 the whole time, so by default every 60 seconds a BGP Keepalive message will be sent through the TCP socket. BGP message type 3 is an update. This is the message that transmits the network layer reachability information. Now that phrase, network layer reachability information, NLRI, used to scare me. It's a big and complex phrase, but it's just a complicated way of saying the IP prefix and length. So for example, 10.130.3.0/24 is network layer reachability information. It's what you can reach. The update also includes path attributes, which is information about each route, and we'll go into attributes in some detail. And it might include withdrawn routes. For example, 172.16.5.128/25 is no longer reachable via this path, so delete it from your table. That's the BGP message type 3 update. And you know, that's the most complicated BGP message there is. It's the routing information, what prefixes you can reach, and the attributes that have information about each route. BGP message type 4, notification. It terminates or rejects a BGP connection, can include an error message, such as BGP version not supported. That's it. Okay, so that's the 4 BGP message types. Opens, Keepalives, updates, and notifications. And that's it. Let's go into the BGP neighbor states. By states, I mean you have a BGP process in your router, and these are the states that the process can be in. The first is idle. When your router boots up, your BGP process just starts up, or a BGP error just occurred. Your BGP process isn't trying to do anything, it's in the idle state. The connect state, that's where you initiate a TCP socket connection request to a neighbor. Active, that's where you're repeatedly trying to attempt to connect to a neighbor via TCP socket. Open sent, that's where you've established a TCP socket to the neighbor, and you've sent your open message and you're waiting for a response. Open confirm. You established the TCP socket to the neighbor, you sent your open message, you got an open response, an open message back. So you've exchanged opens in two directions. And then established. Once you're in open confirm state, and then as soon as you receive a Keepalive or an update, that means you're exchanging data and your BGP neighbor state is established. That's it, the 6 states of the BGP neighbor process. Let's talk a little bit about eBGP and iBGP sessions. Here we have a map with 3 autonomous systems and a total of 5 routers. This router and this router have what's called an eBGP session between them. eBGP means external BGP. That's a BGP session between 2 routers in 2 different autonomous systems. Because this router's in autonomous system 65001 and this router's in autonomous system 65003, they have their BGP session between them is an eBGP session between different autonomous systems. The eBGP session is running on a TCP socket which connects 2 IP addresses. In eBGP, you normally connect the physical IP addresses on the link together. So that way the IP address on this interface will be one endpoint of the TCP socket, and the IP address on this interface will be the endpoint on this end of the TCP socket. Over here, we have a connection between these 2 routers. This is an iBGP session, internal BGP, and that's because it's between 2 routers in the same autonomous system. When you're connecting iBGP, your TCP socket is usually terminated on the loopback addresses on the routers. That way your iBGP session remains up and stable even if a physical link goes down. So typically the IP address of the loopback on this router will be the one endpoint of the TCP socket, and the loopback address on this router will be the endpoint on the other TCP socket. The reason we do that for iBGP is because inside an autonomous system you can have multiple paths to reroute, so you want to be able to do that. But in eBGP, if this link goes down, you want this eBGP link to go down because you want to reroute via some other path. Here's a link which is interesting. This is an iBGP connection between 2 routers inside the same autonomous system. Normally it would be between the 2 loopback addresses in the autonomous system. And you know, these routers don't even have a physical link between them. In fact, in iBGP, you don't need to have physical links between the routers. You just need to have a path so you can get from one loopback to the other. And in general, you're required to have all of your, we'll talk about more the reason for this later, but you're required to have all of your routers have iBGP sessions to all of your other routers inside an autonomous system. So in many cases, you'll have iBGP connections between routers that do not have a direct connection. And over here is another example of an eBGP connection. The physical interface on this IP address and the physical interface on this IP address are the 2 endpoints of the TCP socket. So those are eBGP and iBGP sessions. eBGP is between different autonomous systems, and it's generally the physical interfaces on the links on the physical link between the physical IP addresses on the physical links between the autonomous systems. The iBGP sessions are between 2 routers inside the same autonomous system, and they typically link the loopback addresses inside the autonomous system. Let's talk about BGP attributes. BGP attributes are sent inside BGP updates, which is a 3rd type of BGP message. Each network layer reachability information, each advertised route has attributes. there are different categories of attributes. There are well-known attributes that are understood by all BGP speaking routers. Every BGP speaking router has to understand every well-known attribute. It's required by the protocol. And there are two types of well-known attributes, mandatory and discretionary. A mandatory well-known BGP attribute is attributes that have to be included with every BGP update. A discretionary well-known BGP attribute is an attribute that every router understands, so it's well known, but it does not need to be included in every update. And then there are optional attributes. Optional attributes may not be understood by all BGP speaking routers. There are two types of optional attributes, transitive and non-transitive. A transitive optional attribute, if you don't understand it, you have to pass it on in the updates when you send them out to your neighbors. A non-transitive optional attribute means if you don't understand it, you just drop it, you ignore it, you don't pass it on. Let's talk about the well-known mandatory attributes. These are attributes which every BGP speaking router has to understand, and it has to be included in every update. The first well-known mandatory attribute is the origin. This is something that helps you understand the believability of the information within BGP. The most believable route inside BGP is a route that is originally learned from an IGP. So a route that is expressly originated by the router by configuration. EGP is the next type of origin, and that's the route is originally learned from the exterior gateway protocol, which is the obsolete precursor to BGP. I would not expect to find many routes on the internet today with an origin of EGP. In fact, perhaps I should look sometime. And then incomplete. An origin incomplete is a route that is redistributed from another protocol. So the real origin is not really known by the BGP process. That's the first well-known mandatory attribute. The second well-known mandatory attribute is the AS path, the list of autonomous systems that the route passed through. For example, the AS path for an update might be 7018.3356.10. That means that the route originated in autonomous system 10, which I believe is Carnegie Mellon University, and then it passed through, from autonomous system 10, it passed through autonomous system 3356, which I believe is level 3, and then it passed through 7018, which is AT&T. And then it came to you. So presumably your autonomous system is directly connected to autonomous system 7018. The third well-known mandatory attribute is the next hop, which is the IP address to forward packets to, which is really useful in a routing protocol. The whole point of the routing protocol is to understand, hey, I've got this route, which I've got a packet which is destined for an IP address, I need to know where to send it. Well-known discretionary attributes. Local preference is a well-known discretionary attribute. It's used for route prioritization. Higher is better, the default is 100. Which means that if you don't receive the attribute local pref in the update, then you assume that the local pref is 100. And then atomic aggregate, meaning that the route that you received was summarized at some point in the route. Optional transitive attributes. These are attributes which are not necessarily understood by all routers, but if you don't understand it, then you pass it on in updates to other routers, even though you don't understand it. Aggregator is if a route is summarized, then you have to use the well-known discretionary attribute atomic aggregate. But if you want, you can also put an aggregator attribute in the update, which identifies the router and autonomous system that summarized the route. And that can be helpful for people debugging if you're doing an incorrect summarization. And then a community. A community is like a message, and you can send communities in the updates, and then you can configure routers to listen to particular communities. For example, one thing that's commonly done is you can send a community which says set the local preference to 80, and then on the other side of the of an ISP connection. The ISP might be configured to say, hey, if I receive that particular community, and a community is really just a number when it comes down to it. If I receive community 26, then I will set the local preference to be 80 on any routes that I receive there. So communities are like messages that they can do filtering on. Optional non-transitive attributes. Optional. Not every router understands. Non-transitive. If the router doesn't understand, don't pass it on. If the router does understand, then it knows whatever to do because it understands it. But if the router doesn't understand, don't pass it on. The first optional non-transitive attribute is the multi-exit discriminator. That supplies a metric that allows comparison between multiple paths between the same two autonomous systems. So, for example, if two ISPs connected on the West Coast and on the East Coast, then they might want to send multi-exit discriminators to each other, and that way they'd have some internal metric information. So that way, if your end destination is closer to the West Coast, then you might want to use the West Coast link in order to send that packet to them. The originator ID and cluster list are optional non-transitive attributes that are used by route reflectors. And we'll talk about route reflectors in a later session. BGP decision making. Okay, we've got our routes. We've got our attributes associated with the routes. We definitely have our mandatory attributes, including the autonomous system path, and we might have some other attributes like local pref or med. So we need to make a decision. Which BGP routes, which BGP information prefixes do we actually put into our route table? Because again, that's our destination. We want to get routes into our route table. The BGP table does not forward packets. The route table forwards packets. Well, the first thing I always want to remind you, more specific always wins. A /30 is always more specific than a /20. So it doesn't matter what the metrics are, what the AS path is, what the weight is, what the local preference is. A /30 will always be preferred over a /20 if your IP address matches both prefixes. Weight is something that you can configure locally on a Cisco router to prefer one neighbor over routes you receive from one neighbor over another. It's a Cisco specific, higher wins, and weight trumps everything else. Local preference, higher is better, 100 is default, the higher local preference wins. If you're still in a tie, then you prefer routes originated from an IGP in the local autonomous system number. I won't talk about that today. Maybe we'll do an example of that later. We prefer the shortest AS path attribute. This is the most common thing to make a decision on. The shortest AS path wins. So if the same route has the local pref is not configured, weight is not configured, you're getting it from two different remote autonomous systems. One of them has 4 autonomous systems in the path, one of them has 2 autonomous systems in the path. You're going to prefer the shortest path attribute. So you'll prefer the route that goes through 2 autonomous systems, which makes sense. Because, why go through 4 autonomous systems when you can go through 2? Assuming a tie, you prefer the better origin. So routes that originated from an IGP are superior to routes that you learn via EGP, the exterior gateway protocol, and that's better than routes that were redistributed, so they have the incomplete origin. If you still have a tie, if you're comparing between 2 routes that you get from the different paths into the same remote autonomous system number, then you would compare the multi-exit discriminator metrics. And then eBGP routes are preferred over iBGP routes. And I won't talk about confederations today. We prefer the shortest path to the eBGP next hop. So if you can go, if you have a metric of 5 to get to one eBGP next hop and a metric of 10 to get to the other eBGP next hop, yeah, sure, get out of your autonomous system faster. Take the shortest metric. Then you consider BGP multipath. If you still have a tie at this point, you have 2 paths going to the same remote autonomous system. Maybe you want to install both of them in your route table and do some load balancing. And then if you prefer the lowest BGP router ID, and this one's actually important. A lot of times when you're connecting 2 different Tier 1 remote ISPs, you'll have the same number of AS hops to get to many remote destinations. So oftentimes you'll find that most of your traffic goes to the ISP, which just happens to be assigned the lower number of IP addresses. So level 3 is a lot of IP addresses in the 4net. AT&T is a lot of IP addresses in 12net. So a lot of times your packets might end up going via level 3 as opposed to AT&T just on this tiebreaker. That's BGP route decision making. Let's do some examples. Here's the first decision example. We have two identical routes, two sets of network layer reachability information. It's the same subnet, same /24. The origin is, here's our mandatory attributes. The origin is IGP in both. This one has 3 hops in the AS path. This one has 2 hops in the AS path. This one has a next hop IP address of 10.1.4.4. This one has a next hop IP address of 10.1.3.3. Which one are you going to prefer? You're going to prefer the one on the right because it has a shorter autonomous system path. 2 hops is better than 3 hops. Next example. Here are the mandatory attributes again. The autonomous system, similar to the question in the last problem, 2/24 is the same. Origin is IGP in both cases. The autonomous system path is 2 hops in each case. Which one are you going to prefer? Well, you're going to prefer example number 2 because the next hop IP address is lower, 10.1.3.3. Next example. Here we have an optional attribute. It's well known. It's the local preference. So /24 AS path is the same, 2 hops in each case. Although local preference actually trumps that. Local preference is the highest thing compared to wait. So we're going to prefer the link on the left because it is a local preference of 110. The link on the right does not, or the path on the right doesn't. We did not get an attribute for local preference, so the default is 100. And with local preference, higher wins. So we prefer the one on the left. Example number 4. Again, 2/24s, same origin. AS path is 2 hops in each case. Next hop IP address, and then local preference. Well, in our decision making, we start out with wait, and then comes local preference. So the one on the right is going to win because the default local preference is in effect 100. So 100 is bigger than 90. So our next hop is going to be 10.1.3.3. Okay, BGP route advertisement rules. I talked about eBGP neighbors and iBGP neighbors. eBGP neighbors, the first rule is you only advertise the BGP route that you prefer. So you receive your BGP routes from all of your neighbors, you pick one, you install it in your routing table. That's the only route that you're going to consider to pass on to your peers. If you learned the route from eBGP, you will advertise it to all peers, eBGP and iBGP peers. If you learn the route from iBGP, you will advertise it to eBGP peers only. So let's give an example. Here's a route which comes in from this autonomous system to this autonomous system. It comes in, the BGP update comes in through an eBGP peer. So again, going back, if you learn the route from eBGP, you advertise to all peers. So this router will advertise that route to all of its peers, and it has 2 other peers that it did not receive the route from. So it sends it via both iBGP peers to this router and to this router. Now this router, it received the route from an iBGP peer, so it advertises to eBGP peers only. So it received the route from this router, it will send it on to this router, but it will not send it to the bottom router, because the bottom router is an iBGP peer with this left router. Meanwhile, this router here at the bottom, it received the route via an iBGP peer. It's going to send it to eBGP peers only, but it doesn't have any eBGP peers, so it's not going to send it anywhere else. So what's the end result? The route, the update made it to every router in our routing domain. And it made it to each router exactly once, which is the goal. Great. Let's look at a route advertisement rule broken. Here, these 2 routes, you think that this might work because every router is connected to the BGP domain. But we've got a problem. this router and this router do not have an iBGP connection. So you think that, hey, the route might get there through this iBGP connection and then come here through this iBGP connection. Well, it won't. The route is received by this router. It was received on an eBGP connection, so it sends the route of the update to all of its peers. But it only has one over here. This router received it from an iBGP connection, so the rule is it only sends the update to eBGP peers. So it sends the route up here. Nobody sends the route here. Nobody sends the route to this router. So as a result, this router does not know how to get to 10.35.3.0, which is going to result in a routing problem, because if there's a packet on this router that's destined for 10.35.3.0, it's going to go to this router, and then it's going to go to this router, and this router is going to try to send it over here via this router, and as soon as the packet gets to this router doesn't know how to get to 10.35.3.0, and it's going to drop the packet. So you're going to black hole traffic because your BGP configuration is incorrect, because you don't have an iBGP connection between all of your routers. What does this mean? This means that in iBGP, you need to have all your routers configured in a full mesh. Every router in your iBGP domain has to be an iBGP peer with every other BGP-speaking router in your domain. That way, routes come in from the eBGP peer, and then that router sends the update to every router in your domain via iBGP, because it's an iBGP neighbor with all of your internal routers. We'll go through some examples of that. So what BGP neighbor relationships are needed? eBGP. Configure a neighbor on each physical link between two autonomous systems. If the physical link goes down, then the eBGP neighbor relationship goes down, which is what you want. You want to reroute around physical link failures. But inside your autonomous system, you run iBGP. All BGP routers within an autonomous system have to peer with every other router in a full mesh. Now, why do we even have this rule in the first place? The reason we have this rule is to prevent routing loops. Between autonomous systems, we prevent routing loops by appending your autonomous system number to the path when it leaves your autonomous system. And then if you receive a route from another if you receive an update from another autonomous system with your own AS number in the path, then you ignore it. That's how you avoid loops between autonomous systems. But within autonomous systems, you don't have that ability. So within an autonomous system, the way you avoid the loop is by not forwarding updates in a loop. If you receive it if you receive an update via iBGP, you don't send it via iBGP. So as a result, no looping. But again, that requires the full mesh of iBGP connection sockets, whether routers are directly connected, as in here to here, or not, as in here to here. Let's talk about adding the autonomous system path when the route leaves your autonomous system. Here we have a route that originated in ISP2, which is Autonomous System 65002. The route left Autonomous System 2, and so Autonomous System 2 appends its own autonomous system number to the AS path. And then inside iBGP, inside 65003, the update propagates, but there's no change to the autonomous system path. And then when this router advertises the update outside of the autonomous system via eBGP, it will append its own autonomous system, 65003, to the front of the AS path. Then 65001 autonomous system 65001 receives the update. It looks for its own autonomous system number in the path. It says is 65001 in the path? No, it is not, so I will accept that route. Okay, let's talk a little bit about why BGP expertise is rare. Even large enterprises make BGP changes rarely. If you really want to get a lot of BGP experience, you got to work in an ISP or you got to do your work in the lab. Another reason why BGP expertise is rare is because errors in configuring BGP can have global consequences. For example, 2 weeks ago, a Pakistan ISP made an error in their BGP configuration. They were trying to block traffic to YouTube, And instead of blocking traffic to YouTube inside of Pakistan, they blocked traffic to YouTube on the entire planet by advertising a bad route to YouTube. So you generally don't let your junior network administrators play with your BGP config in production, and because if they mess up, it can have global consequences. But the consequence of that is that they don't get much BGP experience. If you're always having your senior guys do your BGP work, well, guess what? Your junior guys aren't going to learn BGP. In addition, BGP works vastly different from IGPs. Even the network statement means something completely different in BGP. In IGPs like RIP and OSPF, the network statement's used to turn on the routing protocol on the interfaces. In BGP, it helps define what routes you originate. So you might have a lot of experience with interior gateway protocols, but that experience is not very helpful when dealing with BGP. So that's why BGP expertise is rare, why a lot of people think of BGP as a black art, so to speak, but BGP is, which is why, that's why people don't mess with BGP that much. But the thing is, BGP is still a simple protocol. Now, I'm certain that you're a little bit confused since I've covered all these topics today. My suggestion is that you watch this podcast twice. Once now, and then watch about 3 or 4 of my upcoming hands-on exercises where I'll revisit these topics with solid examples in the best hands-on training way, and then come back and watch this again, and it'll make a lot more sense. But believe it, BGP is a simple protocol. You just have to get there and play with it and see it. Okay, that's it for today. Again, I'll be putting a PDF of this session on my website. Thank you.